Welcome back, geologists, for part 2 of the Quaternary plate tectonics. Let's get started. So glacial moraines are just one piece of evidence, and I'm going to be going through all the evidence, and I shouldn't say all, most of the evidence that at least was presented in your book, and there's more to the story than even what we're covering here. This is the abbreviated version. So there's so much proof out there, and remember, the glaciers are gone, so we have to look at what's out there that can prove that they once existed. The most compelling proof are terminal moraines, which are a type of end moraine which represents the furthest travel extent of a glacier. Also important are recessional moraines, where these moraines, as the glaciers retreated, left behind piles of sediment. So you can see the end moraines in the dark green represent the Wisconsin ice packs, and then the lighter shades of green represent the Illinoisan. So there was actually a little bit of ice packs that went further south that are part of that A through K that went through the northeastern part of Kansas and then throughout Nebraska. So Nebraska is highly sculpted out from glaciation if you ever make a visit through where they do most of their crop growing there. Glacial erratics are one of my favorite pieces of proof, and these glacial erratics are big rocks, can be smaller rocks, but most of them are boulder size. Some are house size, for that matter, that were picked up by glaciers and moved and dropped when the glacier melted. They represent rock a good distance away from the source rock. Glacial striations are very important for determining travel direction of glaciers, and these are some glacier striations from Exit Glacier in Alaska. And we can use glacial striations, and have throughout geologic past, like in Gondwanaland, for example, to determine the direction of flow of glaciers from a central location outward in that time frame, like during the Ordovician, for example. But we certainly can do that with Pleistocene aged glaciers, where you can see where the rocks had been at the bottom of the bedrock and they scratched as they're going along that ice that has those rocks embedded in them, and they scour the rocks beneath them. The next bit of evidence I'll be sharing with you for a few minutes is all valley glacier related, and then I'll move into some continental and then shared types of evidence from both valley and continental type glaciers. U-shaped valleys are characteristic of valley glaciers only, and this is like a perfect U-shaped valley at Mini Glacier in Glacier National Park, the RU site of the International Peace Park. And it's just phenomenal, by the way. That's a glacial lake right there that you're seeing. So there used to be a huge glacier, and the glacier probably came from about here to here or higher in the last ice age. So whenever you see a U-shaped valley, that's an immediate clue. Ice used to be there. That was valley glacier. Hanging valleys are totally related to ancient glaciation and probably even recent glaciation, which is certainly the case for the Pleistocene. This is again in Glacier National Park. And a hanging valley represents where the tributary floor is higher than where the main valley floor exists today, and they usually make beautiful waterfalls, certainly the case in Glacier National Park as you look at it. So you can see an active glacier here, it's melting, here's a hanging valley, here's a hanging valley, here's a hanging valley right here, and it cascades this beautiful waterfall all the way down to the bottom of where the actual valley floor exists today. Continental glaciers can't make this, only valley glaciers. Cirques are another one. These are fun things. I like them. It's where the heads of valley glaciers used to be, and the ice comes out from that. If you like to bowl ski, that's what these are. I mean, bowl skiing is where cirques are filled up with snow. Understand that they're not structurally that stable. They've been cracked and fractured and faulted, and so avalanches are common in those areas, but cirques are representative of valley glaciers. Arêtes are another very common feature that are created when multiple valley glaciers carve down the same mountain edge. So I have glacier here in the Southern Alps and one over here. This is in New Zealand, by the way, where Milford Sound is. And see this sharp ridge right here? That is the arête itself. So the rugged terrain of many mountains is created by arêtes. In this case, we got current ice there, but let's say the ice is missing completely and you're left behind with that sharp edge. That would tell you that glaciation had been there in prior geologic time. Glacial horns are probably the most dramatic valley glacier feature that are left behind. That's where you get multiple valley glaciers that carve the same mountain all the way around. And this is one that's in Glacier National Park, and horns are distinctive to valley glaciers, cannot be formed any other way. So there's no snow, ice doing the work there anymore. However, we got this remarkable structure that was carved down by the last ice age. It's just a clue. Fiords have got to be my absolutely favorite next to glacial erratics, and the reason is they're stunning. Fiords are ancient U-shaped valleys that get flooded out as sea level rises after an ice age and floods out that U-shaped valley. So you're looking at the steep walls of the U-shaped valley. So if you continued underwater, there would be a deep ravine there with a flat U-shaped bottom. And these are very common in any area that had extensive glaciation, especially near the sea. This one is Milford Sound, which happens to be the scene of the last movie of Return of the Kings for Lord of the Rings. And so this is in the southern island of New Zealand, and Milford Sound is knock your socks off gorgeous. Probably the prettiest place I've ever traveled to in my entire life. And so fjords have a dear place in my heart because I've seen a number of them in my travels, and none of them have been ugly. They're all beautiful. And you'll see hanging valleys, Cirques, you'll see U-shaped valleys, you'll see it all, usually in a fjord area. All right, continental glacier landscapes don't tend to be that impressive, but don't ever forget about the importance that they bring to us for economic gain. They create things like Kames, eskers, drumlins, kettle ponds, things that are ice-scoured landscapes that are large-scale areas that had thick deposition of braided streams that came out from the melting of continental glaciers. So this one's in Montana, and this was at the base of the Cordilleran ice sheet that we learned about earlier. So this would be continental glacier deposits. Okay, a new piece of evidence. You're like, I knew about all that stuff, but I don't know about pollen analysis. Well, glaciers can be determined their presence by simply looking at the seeds of male producing pollen grains. And so what will happen is this male part of the grain, the pollen, has a nice coating that endures very well in the fossil record. And what will happen as the seed plants get scattered by wind, they end up taking root in the depositional environment in which they can survive. So if we can find these ancient pollen grains, like you see right here under magnification, under a scanning electron microscope, then we can identify not just what plants were there, but piece together a story about the ecosystem and climate of the region. Seawater gives us another interesting clue that glaciers used to be there. Now, seawater should always have a higher ratio of O18 than O16. So we're talking about oxygen isotopes here. Why is that? O16 evaporates more easily, so we find a higher concentration of that in glacial ice as we do in seawater. That's important because as you see declining O16 percentages and the rise of O18 seawater, we know that during glacial times that we should see that documented and the animals that built their shells from this material. And sure enough, we do in foraminifera shells. In addition to oxygen isotopes, forams give us another special clue into the last ice age. So what will happen is a certain type of species of forams coils to the right during warmer conditions that are above 10 degrees Celsius, and then you will see it somewhere between 8 and 10 degrees Celsius. If it's below that temperature range, it will start coiling to the left. And this is unique, so we can look for the specific foraminifera and be able to determine cycles of ice ages simply by looking at this one little species of foram. Go figure, right? Bet that was a surprise. You've learned about Varves and Dropstones. Well, these can be created in both continental and valley type situations, but something you may not know is that the Varves, which are the seasonal deposition of the lake actually have dark and light laminate layers. That actually means something. The light ones or layers are made up of silt and clay during spring and summer seasons, while the dark one represents more organic matter and the finer grain, such as really fine grained silts and shale deposits that are laid down during the winter months when the ice of the lake has been built over that lake during the winter months. Then, of course, dropstones represent icebergs that have broken off, calved off, and a rock, as the ice melts, drops into the middle of that fine-grained sediments. So if you have a high concentration of dropstones, you're looking at a higher probability of warming trends, not just seasonal, but even warming trends. So another piece of proof that we haven't talked about in physical are the scablands. Well, the scablands are located up near Oregon and Washington State, specifically Washington State. And here's what happened is the Cordilleran ice sheet came down into Washington State and parts of Montana. It would melt much quicker than we would see the Laurentide ice sheet melt. And a number of these areas had glacial dams that filled up some pretty big glacial lakes. And as these things catastrophically flooded and melted, they scoured out the land. So you're actually looking at something like this coming from this direction down, and it's eroding out, causing flash flooding to occur. Some serious bad floods occurred in the western area, the Craton, as a consequence, and we call this region the Scablands. Pluvial, and make sure you see that with a P as in power instead of F as in fluvial. These are areas that were landlocked basins that filled up with rainwater during the wetter periods of glacial times. If you think back to physical geology, we talked about that you needed two conditions to form glaciers: cool enough temperatures and wet enough climate, right? So one without the other, you really don't get glacial advances because the budget of the glacier can't grow. But if you get wet enough and cool enough temperatures, you can start to do that. So the Ice Age would have had wet conditions during glacial cycles that could produce snow that would crystallize or recrystallize into firm. So after the last ice age was over, these little blue things that you see all over, so you can see where it says Pleistocene lakes, and then the light blue, like this one, Great Salt Lake right here, are modern day lakes. Here's a modern day lake right here. But all of these are pluvial lakes. And these pluvial lakes have evaporated. Some of them are actually important because they contain things like halite deposits and gypsum deposits that were associated with these last ice age systems that produced an extensive amount of evaporite deposits. Lake Bonneville is important to talk about because a lot of people think it still exists. There's only really one section that does, and that's the dried up section that makes up the Great Salt Lake. In short, this was a huge surface area of a lake that was over 50,000 squared kilometers in size and over 1,000 feet deep. And it had natural moraine dams that formed to kind of keep the water intact. And when it catastrophically failed, it failed about 15,000 years ago at Red Rock Pass in Idaho, which is a tourist stop now, by the way. And keep in mind that this thing would have been discharging immediately. It'd be like a lake in your city that's dammed up by a man-made dam, catastrophically failing because the dam breaks open. You could imagine the devastation that this would have caused. When it broke, it discharged at about 1.3 cubic kilometers per hour. That's pretty remarkably fast. So as the lake dried up, it left behind huge salt deposits, which is where the salt comes from Great Salt Lake in Salt Lake City today. Well, there's an even bigger lake that formed called Lake Missoula, and this is in Montana. And this particular lake had a flood discharge about 30 times the strength of what we just saw with Lake Bonneville. This was super important to forming the scablands, and this is where it actually would have broken open. And so this process here, when you look at these big lakes like this, it tells a story that adds to the many pieces of proof that we had that there were glaciers in the last ice age. The Great Lakes are also a story to talk about of glacial evidence from the last ice age. So how did they get there? First of all, they're formed by the Laurentide ice sheet. So as the ice sheet came in and out throughout those cycles that we've been talking about, the weight of the ice depressed the land and it scoured out the land. And as this happened about 20,000 years ago, during the last major flux of the Wisconsin ice sheet, the glaciers there were up to 2 miles thick. That is a substantial weight, and they gouged and depressed the land, and when they did, they created lake basins known as the Great Lakes. So at the conclusion of the Ice Age, these are going to fill up by rainfall and melting glaciers, and that's how we have the Great Lakes and what they're made out of today. Another important piece of proof we have is isostatic rebound. I always use the example of the couch from my first dentist appointment to get a filling, and I was booted off of the love seat when a person of substantial size got that couch, and I had to play on the floor. And they got called back before I did, and when they got up, I was just mesmerized by the fact that there was a huge indentation in the cushion, and I was like, Mom, take a look at this. The couch, it's got a hole in it. And, this person just thought I was, like, awful. I didn't care about the size of the person. I was worried about the couch seat. I was going to be interested to see how this thing got back to its original shape. And sure enough, about half an hour later, it popped back into position, and I was like, Mom, look at the couch. It's rescued. It's saved. And she's like, sure, that's isostatic rebound. And I'm like, huh? What's isostatic rebound? She goes, you just saw it. You just saw something heavy leave a depression and it popped back into place. Now, keep in mind, my mom's a scientist, so it's not beyond her to do something like this. But that's what happened with these ice packs. They weighed huge amounts of weights, and they depressed this crust. And since they weighed so much, the lithosphere would try to find equilibrium with the mantle. And when that ice sheet was present and the extra weight was there, as it melted off, the land no longer has that weight. So it tries to find re-equilibrium with the mantle below and starts to pop back into position. In some cases, this has meant around 1,000 feet of rebound in the last 10,000 years. That's pretty darn impressive. Probably the most famous place this happens is in Scandinavia and Hudson Bay. We can say that the natural cycle of climate change has a distinctive interval of time that I think is important to discuss about ice ages. Typically, the ice age themselves last about 100,000 year cycle. That not just corresponds to something we'll be talking about in a minute with the Milankovitch cycles, it also corresponds to ice core data, especially from Greenland and Antarctica. So we can see that there's a lot larger stretch of time for the ice age and then a narrow window of time for the warming cycles in between. So every glacial period is followed by an interglacial period, which is the warming cycle, which is what we're in right now. So it's about an 80 to 20% ratio. So out of that 100,000 years, 80% of it probably was ice related, and 20,000 years or less would have been the interglacial period from what we can see. So these pink spikes would have represented interglacial periods of time, and the big blue sections represent the ice age fluxes. So we're definitely have a trend for longer ice ages than we do interglacial periods, and I think that's important for you to know. Milutin Milankovitch came up with models of mathematical models, that is, and he's really an astronomer that did all this complex math, and most astronomers are physics people that deal with high-level mathematics. And essentially, he came up with 3 distinctive factors that could influence or help trigger the onset of major glaciation if they were to occur as a group. The eccentricity cycle has to deal with how elliptical or circular our orbit is. At first glance, we would want to say that the more elliptical it is, the more chance we would have for forming ice during the winters. Now, you're somewhat right about that. So let me talk about this one, because I think this is probably the most substantial of the 3, but coupled with the other 2 that have significant impact to solar radiation absorbed at the polar regions of the Northern Hemisphere, answer the rest of the story. So when the Earth's orbit is more elliptical, we spend less time close to the sun in the span of 1 year. That's correct. You are absolutely right on that. However, as we're approaching the sun, where we're closest to the sun, and that's a term you need to know called perihelion. When we're furthest from the sun, that's called aphelion. So perihelion represents when we're making this route right in here, this would be perihelion, we're going to have warmer summers. So this would also mean the potential to melt glaciers. So if I have a more circular orbit as opposed to a more flat elliptical one, I have less time going around the circle right here that I'm going to be close to the sun. So while I may not have as extreme a winter, I will have cooler summers, which means less potential to melt that ice. So the more elliptical, the closer the approach we are to the sun, the more melting of glaciers occurs. So in ice age, you would be looking for a rounder orbit as opposed to an elliptical orbit. To make this from more elliptical to more round, that cycle takes about 100,000 years, and interestingly enough has been validated in ice-scoured data that's been taken in Greenland and Antarctica. Well, the axial tilt is sometimes referred to as obliquity. I like axial tilt better. It's easier to understand. So basically, our Earth sits on an axis, and we can fluctuate from about 2.5 degrees. Currently, we set at 23.5 degrees, and then we can vary as low as 22 and as high as 24.5 degrees. So the variation from max of 24.5 to the lowest degree angle of 22, that cycle takes about 41,000 years to reach that maximum extreme on either side. When we have a decreased axial tilt closer to the 22-ish degree area, this will cause the sun's solar radiation to be more evenly distributed between winter and summer. But you're like, okay, well, that means that we'll have more equitable conditions. Let's just think about this for a minute. Less tilt also decreases the direct solar radiation seen and absorbed at the polar region. So while you may be correct in saying that that would be more equitable, I think you're thinking about the equatorial regions. So be careful on that to realize that we're talking about polar specifically in the Northern Hemisphere. So if we have decreased axial tilt, again, closer to the 22 degrees, this would promote the growth of ice sheets. And we'd have a warmer winter, but hold on to the more moisture, which is important for making glaciers, right? And we would have more snowfall if we had higher moisture content, because the hydrosphere would have more ability to hold on to that moisture. So the summer temperatures are cooler and not as able to melt those glaciers. So the lower the degree of tilt, the more potential for ice age. The last one's kind of fun. It's called the precession of equinoxes, and more easy to understand is just how the Earth wobbles on its axis, different from what we just looked at. When the Earth is closest to the sun, again, that's perihelion, there will be an increase in summer solar radiation, obviously, but a cooler winter in one hemisphere, and the other hemisphere will be the opposite. You have a warmer winter with a cooler summer. So right now we're at perihelion. So if we are at aphelion, far away from the sun, and it's during the winter months, then we'll have less radiation altogether. And so we'll have longer, cooler winters. And at the polar regions, that's darker as well. So if you've ever been to a place like Antarctica or Iceland, and in my case, I've also been down in the Southern Hemisphere, down in New Zealand, I can tell you, especially in Iceland and Alaska, they had about 22 hours of daylight during the summer. It drove me crazy because I can require almost complete blackout to sleep. So in the winter, it's directly the opposite. They have twilight for their daylight hours and then darkness for most of the day. So this is important. So you take all three of these together. I need you to think about this. If I have a longer, cooler, colder winter because of the the precession of equinoxes, which is the wobble. And I have an axial tilt that's lower degrees. That means the Northern Hemisphere has less direct solar radiation. And I have a more circular orbit in which I have less chance to be closer to the sun. All three of those things means promotion of glacial growth. Very rarely do we see all three align simultaneously, but this happened in the last ice age multiple times. And so this was what Milankovitch showed in mathematics, and it's now considered a very viable theory and accepted by scientists across the globe. So what caused the Pleistocene glaciers? Just the story I said. All three of those things, or those cycles, happened together, and that gave the Northern Hemisphere less direct solar radiation and insolation. And the polar regions would have received the blunt end of this. That's why you see most of the glaciation coming from the Arctic Circle and, of course, the Antarctic area. But especially in the Northern Hemisphere, where glaciation has been very rare, this now had the perfect situation to make that happen. So you'll get your snow accumulating in the winter, and the cooler summers can't melt them, so the snow recrystallizes into firn, and you start getting glacial advances over a long stretch of time. If you go back to that, the cycles are about 100,000 years long. So let's take a look at the plate tectonics overview of the Quaternary. Take a look at that gorgeous picture up there in the right-hand corner. I took that going on towards a cruise in Alaska, and you had to take a bus from Anchorage to Portage, where you actually port out. And this was our bus stop. So if you end up taking a tour by cruise boat up or down the Inner Passage, you'll likely go to this spot. And you have the choice of going to a convenience store to get candy, or pay your bus driver a $10 tip so you can go see this instead. It's actually a preserve, nature preserve, and there are lots of cool animals to see too. And let me tell you what, it's just going to be worth your stop. You will be glad you did. I took that with an iPhone, so that's pretty impressive, right? Gorgeous landscape, and that's a modern day development of glaciers, but I can tell you that it was impacted in the last ice age because of the Arêtes that you see right here in the big U-shaped valley. There's a little ice left, but the ice was way up here in the last ice age. So a few things to keep in mind about the Quaternary. We had active volcanism in the Cascadia Range and still do today. Because remember, Holocene, current day, most recent, literally recent, right? Totally recent. It's still happening before our eyes. Rifting and started in the Neogene, continued on through the Quaternary, and is still happening today in the Rio Grande Rift region. We reactivated faults as some of this crustal movement would occur, and that activated the Grand Teton Fault, which made the range look the way it does today. Yellowstone had some incredibly important eruptions that definitely could have played into ecosystems and weather patterns at that time, certainly climate conditions. Grand Canyon erosion began about 6 million years ago, and we experienced the last ice age, which included 13 different sequences of movements of ice advances and interglacial periods. We have a whole slew of proof that we listed, all the way from Valley Glacier proof to continental deposits and landforms, and then we certainly talked about some of those weird things like pollen seeds and foraminifera coiling directions and the ability of 018 to 016 ratios, things that you may not have known before you got into this lesson. So I'm really looking forward to getting back with you to share the life animals and the evolution of mammalian history that's going to occur during the Cenozoic, and then also talking about hominids. So looking forward to seeing you back in our next set of lectures, which is all about the rest of the story. Good place to take a break, and I'll see you back at our next lecture. Bye.